Hello again, all you beautiful people. It's that magical time. That's right. It's time for our third Numpy tutorial. It's 6 o'clock in Connecticut, and we're expecting over a foot of snow tonight, so I'm hoping I can get this done before the power goes out. Let's see if we can make it through. So, first thing I'm going to do is tell you what this video is going to be about, and not delete that. This video will be about accessing vertex data on a mesh inside of Blender, doing some math on that vertex data, writing that data back to the mesh. So, first thing you want to do is import, actually BPY, which is Blender's Python. We're going to import numpy as np, as per usual. And we need to have an object in this scene that we can do something with. So I'm just going to hit Shift-A and add a monkey. And it's over there. Alt-G, declare its location, just so that it's in the center. And make this a little bit bigger for a second. Now, this object has a mesh associated with it, and the mesh has data associated with it. Inside of that data is included the locations of each vertex. Now, it's one of my personal pet peeves, a vertex, some vertices. I hear people say a vertice, and it drives me mad because there is no such word as vertice. There is a vertex and some vertices. Okay, glad that's out of the way. Now, when you select these vertices, or a vertex, you'll see the locations popping up over here. And I think, yeah, you can actually change them there. That's cool. I didn't realize you could do that. What we're going to do is we're going to take a NumPy array and we're going to fill it with the locations of every vertex. So, to do that, I prefer to build a function. So in Python, to build a function, you do def and you call your function something. We're going to call it getCo, and then you do arguments. And this one is going to take one argument, and it's going to be the object. And remember, this function is going to take the vertex locations and build a NumPy array for us. So in order to build a NumPy array, well, actually, in order to quickly access the vertex locations without having to do a Python loop, we're going to allocate our memory first. So each vertex has 3 values, which means we need, and these values are floats, which means that we need 3 floats for every vertex. So we start by getting the vertex count. So v count, and we're going to use Python's len function, and we're going to do ob, which is our object. It will be our object, and we're going to do the object's data, and we're going to do the vertices. All right. So this is the first part, and just to make sure that we're doing things right, we're going to say our object in this case is going to be just the active object in the scene. And to get the active object, we're going to make ob equals bpy.context.object. And then we're going to call our function, getCo. And remember, our function takes one argument, which is the object, and we just created that variable. And then to see something happen, we're going to have it print this vCount. Alright, and if I didn't do anything silly, if I did, you probably saw it just now and you're going, that guy, he just wrote that variable wrong, or forgot a colon, or I don't know, something. Anyway, okay, it worked. So we have 507 vertices inside of our Suzanne mesh. And if you look up here, you see the same number, 507. I don't know if you can see that on your screen, but you'll just have to take my word for it. And if you're not okay with that, then you probably have bigger problems. So, we've got our v count. Now we're going to allocate some memory using this lovely little number we've just generated. So we're going to create a NumPy array, and it could be an empty array, it could be zeros, it could be ones. As long as it's a float array, and as long as it has the right number of elements, the right amount of memory that's allocated, it should work. So we could do we're going to start by saying CO equals, because ultimately we're going to return our CO, which is going to be the coordinates of all of our vertices. So CO equals np dot zeros, and it's going to be v count. Now remember, there's 3 floats for every vertex, so it's going to be v count times 3. Now, to show you what np.zeros does, I'm going to go down here to the interactive console real quick. I'm going to do import numpy as np, and then we're going to do x equals np.zeros, and we're going to say 10. And then x is going to be an array full of 10 zeros. Simple enough. You can also do x equals np.ones and 10. Well, let's do something different. 4. And now x is for ones. You can also declare the data type, so x equals np.ones 5, and it's going to be equals np.int 32. So now we have 4 ints. So np.ones, np.zeros does that. You can do np.empty and put in a value and declare the data type. dtype equals dot float 64, and we get empty for dtype equals mp.float64. It created ones. I don't know what would happen if we did it with like int 32. np.empty int 32. It creates just allocated memory with weird values. But it doesn't really matter because all it's doing is just allocating memory. So up here we've got our CO is our coordinates, and np.zeros v count times 3. We've allocated enough memory to fill with the vertex locations for every vertex in this monkey. So now Blender's got a fast access to its collection properties, which is the for each get method. And most of Blender's collections have a for each get method, which lets you quickly fill an array with data without having to loop through it in Python. So it's almost as fast as native C. So our for each get method is underneath the vertices. So we're gonna do ob.data.vertices.for each get, and this takes 2 arguments. It takes the category, or it's a key, which in this case the key is CO, and it takes the array, which we've already created the array, and it's also called CO. Now if we do, we're going to print out CO. If we print CO above, we're going to get a bunch of zeros, and then we do this for each get method, and it actually overwrites the allocated memory with the vertex locations. So then if we print CO again, so let's do, this is CO before, and this is CO after. Alright, now when we run this, we get over here in our Python our console window, system console window, we get this thing that's annoying me because I'm apparently OCD. It starts out as zeros, and then you get the locations of these vertices. Now Numpy automatically puts these dot dot dots in here because it doesn't want to print the whole thing. If you wanted to, you could do inco print I and force it to print the whole thing, and then you get every value in here, which is pretty ridiculous. And I did that just so you could see that it's basically just giving you an appended, or what is the word I'm looking for? An abbreviated version of the NumPy array so that it doesn't print everything. There is an option if you go into the numpy.org and look at how to set the print default settings. You can set it to print the entire array by default. I will probably look at that later as we get into some more complicated stuff, or you can just go and look it up right now if you can't stand the thought of not knowing that right this second. Alright, so we've already got our array full of vertex locations, and they're a little hard to look at because it's just a flattened array. And really, it would make more sense to have them grouped in sets of 3 because we're working with vertex locations that consist of 3 floats. So we talked about reshaping in the last tutorial, and we're going to reshape this array so that it looks a little bit cleaner, and also because there's certain operations of math that we want to do on it that are much easier if we change the shape. So we're going to say co.shape is now vcount, so that we'll have our first shape is going to be the number of vertices, and our second shape is going to be 3 because it's 3 floats per vector. Alright, now when we print CO, we get this lovely thing, which is the n by 3 array. And what is it? 507. So the shape of this array is now going to be 507 by 3. Print co.shape. And you get this tuple down here, 507, 3. Alright, so that part is out of the way. We have our lovely array full of the vertex locations, and we can do some math on it. Now, down here where we are calling this, we want to be able to actually use it. So we're going to say co equals get co and ob. And we already know ob is the active object. Alright, we don't need these print statements anymore, but we do want to get this array of vertex locations, so we're going to return it and spell it correctly. Because I've found that computers don't understand what you mean. They only understand what you tell them. They're a lot like people. So, return CO. Okay, spelled correctly. Now, print, just to make sure, CO, and run it. Yep, we still have our coordinates there. So now what we want to do is something. And by something I mean some math. So we're going to take the location of every vertex here and add something to it. So for example, we're going to do transform equals, and we're going to do another NumPy array. And we're just going to make an array, and well, you know what, let's do this. 0, 0, and 1. Okay, now we're going to say CO plus equals trans. Now NumPy knows automatically that we have an n by 3 array of floats. This is by default going to turn it into a float 64 array because that's what it does by default. We can specify the data type just to be sure. p.dtype equals, and I'm going to do float 32 because, believe it or not, it's actually faster with float 32 than it is with float 64. So I generally do everything with float 32. In fact, like this one up here, I would say dtype equals float 32. I generally like to do that. And if you declare your dtypes when your data types when you're allocating your memory, and you know the level of precision that you need, and you want it to run fast, on my system at least, the data type of float 32 with NumPy performs faster than any other data type for floats. So if you did float 16, it takes longer. For some reason, it's more efficient with float 32. It's also more efficient with float 32 than it is with float 64. Sometimes you want extra precision, so that's up to your judgment. Depends on the project you're working on. Alright, so we've got our CO now plus equals this np.array001. And what that's going to do is it's going to move everything up on the z-axis by 1 Blender unit. Now, if we run this right now, it has an error. What did I do? Line 24. np.array 1. Keyword can't be an expression. np.dtype equals np.float32. That's what I missed. Don't forget that. Line 24 again. Trans equals np.array 001. Oh yeah, I put the np dot at the wrong place there. Is that right? Yeah, okay, I got that right. Yeah, don't make that mistake. Alright, so now we are adding this, and the array is actually changing, but nothing else is happening because all we've done is change this allocated memory. We haven't told it to write that information back to the object. So in order to write that information back to the object, well, just like you've got the for each get method, we have a fast way of overwriting Blender's collection, and that is for each set. So for each get and for each set. So we're going to say ob.data.vertices.for each set. And it works the same way. The first argument is a key, and it's going to index, the key is going to access the coordinates, and we're going to use CO again. And when we run this, you're not going to see anything happen again, except that there's an error. So there are two problems here. The first thing is that Blender uses a flattened array. So when you make your pretty NP array like this, x equals np.arrange, and we're going to do 12, and then we're going to do x.shape equals 4, 3. Now we've got this lovely 4x3 array, and it could be vertex locations that we're dealing with here. Blender's collections use a flattened version of X. So you would need to write this out. Let's say you had a mesh with like a plane that had 4 vertices. Well, you can't write 4 vertices to the plane in this shape. You would have to write them in a flattened shape, because that's the way the Blender for each set method is designed. It just has to have a flattened array. So it would need something like this array before we reshaped it. So we could say x.shape equals, x.shape equals 12 again. And now we've got the flattened array. There's something that I generally use which gives you a view, and you could just overwrite the shape like I just did. I haven't actually speed tested this, so it might be faster to do what I just did. But what I normally do is, well, first of all, let's set the shape back to 4.3. I would just say x.ravel. And when you do x.ravel, it gives you a view of your array. Your array is still the same. It still has this shape. But x.ravel gives you a view of the array as if it were flattened. So that works. There's another Numpy function called flatten, flatten with one n and no m's. And it does the same thing, but if you use flatten, you will actually get a copy of your array. It is not giving you a view. It's not just showing you the array in a different way. It's actually allocating the memory again, generating a new array. So if you're worried about speed, then you don't want to make unnecessary copies. Now you may want to make a copy, and you may want to make a copy that is a flattened version of your array, so you can use x.flatten, numpy.flatten. But for the sake of performance, you generally want to use ravel. So we can't just write our coordinates back to the object here this way. We actually have to do co.ravel. Now we should be able to run this Yeah, with no errors. So we're not getting any errors popping up. You'll notice also that the mesh isn't moving, and that's simply because we may have overwritten the data, but we haven't told it to check to see if the data has been overwritten. So we need to do ob.data update. Is that right? I believe so. Whoa! Yep, there it goes. It moved up. And it will keep moving up as long as we keep doing that. Whee! And you'll notice that the object hasn't moved as far as the object's origin. The object's location is still 0. Wait, that's the 3D cursor. Where's the object? Okay. Yeah, location. The object location is still all zeros. Because we're not moving the object location, we're moving all of the vertices in the object. So let's bring it back down. Minus. Ta-da! Now you can also, like, let's say we do times equals this. Now, I don't know if you can imagine what's going to happen. It's going to flatten it on the XY axis and do nothing on the Z axis because we've just said that the XY values are 0. So it's going to turn it into a really thin line. Here we go. Woo! Thin line. I don't know if that made sense to you, but what we've done, we've taken this object and we've said, take the X value and scale it to 0. 0. And then take the Y value to 0, and you end up with that. So when I multiply every vertex in this object by 0, 0, 1, I've taken X multiplied by 0, Y multiplied by 0, and Z and multiplied by 1, so nothing happens to the Z. We can also do times equals, let's say X is 1, Y is 1, and Z is 2, and we'll set Suzanne back to her normal previous glory, beautiful shape. And now we scale on the Z-axis. And so forth. Now, a lot of programs, a lot of array libraries, by default will do matrix multiplication, which is something different than what Numpy does. Numpy, by default, does simple multiplication, coefficient multiplication, if you will, or maybe arithmetic multiplication. I think it's usually called coefficient multiplication, where it's just, 2 times 2 equals 4, not 2 times 4, 2 times 2 is a dot product thing or something weird. I guess that's it for manipulating geometry. After this, we will do some interesting things with geometry. Now, keep in mind in our very first introduction, we showed that doing the collection property this way, where we create a Numpy array out of the vertex locations, and then we set the vertex locations again with that same Numpy array. When you start getting into big arrays full of data, like meshes, with a million vertices and that kind of thing, the bigger this data set, the more of an advantage you're going to have with Numpy. So if you're working with a mesh that has like 8 vertices and you do this, Numpy is going to be a little bit slower, but you're talking about milliseconds at this point. When you get into arrays with like a million vertices, you're going to end up being like 30, 40, 50 times faster using Numpy. So Numpy is really best at dealing with big arrays full of data, doing one operation on the whole array, and then writing the whole thing back with something that's fast and low level, like for each set. One thing just to note, a thing that you never ever want to do with Numpy, don't ever do Numpy inside of a loop where you access every value inside of Numpy. So like if I, instead of CO plus equals trans right here, or I've let Numpy worry about how to add this value to every value in here, if I did something like for iters in CO, I plus equals trans, you're doing the same kind of thing. You're looping through and you're adding the same value. So the end result is the same, but this is going to be like 100 times slower. I'm exaggerating, but it's going to be considerably slower. So don't ever loop through a Numpy array to try to do math on it. If you're doing that, you're just costing yourself performance. It's really terrible. It's the worst thing you can do with Numpy. There are people who have stopped using Numpy because they think it's slow because they do this kind of thing, and that's not how it's meant to work. Because a Numpy ND array is a fairly complex object that has a lot of attributes, and it's designed to be accessed and work in a certain way. And creating a Numpy array takes time because you're setting up its attributes, you're building an object with a lot of attributes, and you're allocating memory for it. So if you're looping through and you're doing that in every iteration or in several times inside of a loop, then you're just wasting all kinds of time, and you'd be better off just using Python loops and using like the mathutils library or a typical math library. So don't ever do that. In the next tutorial, I think I'll be looking at logic, and we'll be looking at some dot product operations, and we'll talk a little bit about what dot products are used for, and we might do a brief introduction to the closest point on edge function. So until next time, I'll see you after the snow.